Okay, so good evening. So I'll start now. So we were waiting almost 5 minutes. So I will go to the presentation slides now. So I'm Durga Madhav Mishra. So I am now an assistant professor in physics at IIT Jodhpur in the Department of Physics. So I'll be teaching this course Materials Science. The course code is MPH-025, and since the number of students are quite less, so I thought probably in the beginning I will find out like what are the topics probably from this uh, particular subject you are interested in, so that we can spend more time on those topics. So, I mean, those who are present, if you have any wish that we should cover this part more, so I will do that. So, if you have any wish, you can tell me.
Sir, you can first give us a means a overall idea of what are
Hmm.
there in the syllabus.
Okay.
Then,
So, have you, I mean, anyone has gone through the syllabus or course content of this one so far or not?
in the course content chapters are there, but
Hmm.
in there they have given links of NPTEL, some classes.
NPTEL, yes. Hmm.
Those classes links are there, but
Okay.
such the books are not means
Okay. Okay.
not there.
Mm-hmm. Yeah. Okay. So let me first give you the overall course outline that I think one needs to know when, like, as a once complete somebody who completes this course should be able to understand these aspects of material. So we will basically start with material structure and morphology. Then we will delve into materials processing. So the structure. So I will elaborate on some aspect of this bullet points later on, because when you look at all these outline, it is quite vast. So typically, you need to spend at least like 40 to 50 hours lecture hours to really understand this. So now everything is squeezed to only, I think, 8 hours. So we will try, like, what are the important aspects I will try to present here. So uh, so the broad outline is like these points. So material structure and morphology, material processing, then imperfections or defects, let's say, in solids. Then another important aspect in material science is phase transformation. So phase, as you know, like going from a gaseous phase to a liquid phase to a solid phase, and in fact, there is also possibility of going from one particular phase, solid phase, to another solid phase as well. So we'll look at that, what it means. Then, of course, the properties of the material. That is why we are interested in material, first of all, because they have very interesting properties. And of course, finally, their applications. So before we go into the what is a material science and what is why we need to study that, so I just want to give a historical perspective of how materials have shaped our civilization. So if you look at the history, so these different forms of materials actually represent how advanced the civilization is. So over the period of time, so you can see that we started with stone age, where we used tools made from stones, uh, uh, and we used to live in, like, wandering in forests. So there was no so we are just living like animals used to live, or still they are living. So then with time, so we progressed and we could use different tools to make some form of metal, for example. So here, the next age, what is called as a bronze age, so where we could make some form of alloy, for example, by mixing two different metals. Again, there is a level of complexity increased, and also it led to a certain advancement in our civilization, the way we used to live. So similarly, the next is the iron and steel age, where we could make a huge, big structures, industrial scale structures, and that helped us in a lot of like eased our standard of living to a great extent. So that is where the industrialization happened. So we could manufacture things which are not available in nature. So that's why we kind of moved into a very sophisticated form of civilization. Then later on, or let's say when you look at the 21st century, so it is all about digital age. So where we are using laptops, computers, smartphones, I mean all these online conversation that we are having, or we are able to share knowledge online, is possible because of something that we built known as chips, so which we call as the silicon age. So that means our civilization has been defined by what kind of material we have used and how complex we can make it, so that we can advance some form of technology. And that is what somehow one can associate this our civilization with the materials that we have used. So that means the next phase of our civilization, we still don't know what materials will lead in those next stage. So in the next century, for example, so what will be the material that will define our civilization is yet to be decided. But more or less, we know like it could be some form of nanostructure or nanomaterials, or thin film, for example, they'll be particularly uh, will be
Okay,
used.
Sandeep.
But
Yeah,
yes, any
yes,
question?
Sandeep.
No? Okay. So, but what particular any material that is going to play any important role, that is still to be decided. So that actually leaves a lot of scope to know this exact field, so that we know how different materials and technology, or particularly technology, is dependent on materials. So that we should know, and that's why a broad understanding of a material science is required. So I'll give you another interesting example here. So as I like when we are looking at our civilization, so any technology that we are dealing with is basically about some form of material that we can use it in a form for our advantage. So here I'm just giving one simple example. On the left hand side, what you see is a drink which is so here the brand name is used Coca-Cola, but it doesn't matter, any drink, uh, the packaged drink or beverage nowadays that you consume. So it can, you can put it in like a can, or you can put it in a plastic bottle, or you can put it in a form like a glass bottle. So the same drink has can be packaged in three different materials. So that is how we are really close to using many forms of materials in our daily life. So the can, which is made up of aluminium, for example, the plastic, some form of polymer, and glass, of course, it is like silicon dioxide or some form of that. So that means they are really very different types of materials, and we are using it for consuming our food products, for storing our food products. So the right hand example is more towards the future. So when you look at the future computing, so as I said, the digital age is defined based on silicon. So because we could make various chips or semiconductor materials, we can make it in a very different forms, like what we call as a transistor. So that's why we could do computing, processing, and so on really fast, and that has helped us immensely. But in the future, what everyone you must have heard, now the next age will be using quantum computers. So now the quantum computers also needs some kind of materials where they can so instead of using in a classical computer where you use bit, so there you'll be using something called as a quantum bit, so qubit. So now this qubit has to be also built based on some materials. So the possibilities are, the options are many. So one can use, for example, like photonic crystals or materials, optical materials. One can use superconductors. So superconductor, for example, using Josephson junctions or some form of superconductor and semiconductor junctions, one can build. Even one can also build it based on some simple silicon germanium based semiconductor made in a special transistor. uh, One can also look at create some exotic, very interesting particles within a material to produce these qubits and then use it for quantum computing. Then also you can create a very precise defects in solids, and that also you can use for quantum computing. So there are many options. So probably the next age will be defined by the quantum computers, and the best material which can produce these qubits, or where we can control the qubit, probably that will be the future material, I think. So you can see two contrasting example how material is important for our civilization. So with this motivation, so I'll now try to define what material science means. So when you look at the material science, there are these five components that I have made on the top. So the first component, initially the number of components were actually four. So the fifth component has been added, let's say, for last 1 or 2 decades. Okay, so earlier it was not used. So the first component is the processing of the material. So that means how you can produce or make these materials. Okay, that is the most important thing. So what are the technology that we have so that we can fabricate a device or fabricate a material, make a material, so that is quite important. Then, like, what kind of structure that a material can have, so that will also is very important when we look at a material science. So the structure is a very broad term I am using. So if you now dig deeper into the structure, so you can talk about, let's say, a subatomic structure, for example. So subatomic means how the structures are in atomic level. So how the electrons are arranged in an atom around a nucleus. So that will be the subatomic structure. That is definitely going to play an important role. Then there is also the atomic structure. So that means now we are going one level up. So you have made an atom, but now how the structure is when you put more than one atom. So you form a molecule, then you form maybe a bigger molecule, you form a solid, like by putting many atoms. So that is the atomic scale. Then the next hierarchy here will be the nanostructure. So that means you will be making the structure which is, let's say, from 10 nanometer to 100 nanometer range. So in that dimension, so you build materials. So that is a nanostructure. So then the next level is a microstructure, which is typically from few micron up to probably could be up to a few millimeter. So that is also one level of structure that in material science we look at. So similarly, you can also look at the macrostructure, which is basically what you can see with your naked eyes. So it could be from millimeter up to few centimeters or even larger. So there are different levels of structure that needs to be understood when we talk about material science. Now we need to use different tools and techniques to also see those different structures. So for example, if I want to see the nanostructure or microstructure, I pro- if I say, let's say, microstructure, I probably need a optical microscope. I cannot see them with my naked eyes, so I need a optical microscope. So similarly, if I want to see a nanostructure, I will want to use a even make it higher resolution, because the sizes are small. So that means I would need, for example, like a electron microscope, so where I'll use electrons to perform the microscopy. So similarly, the atomic and subatomic structures you can investigate may not be directly. So possibility is there. You can use a transmission electron microscope, but also you can probe indirectly these structure as well. So this is important. And why structure is important? Because the structure at each level will decide what the properties of the material are. Okay, so the property is the third component here, and property is what we are always interested in. So this is like mechanical property or electrical property or the thermal or magnetic, optical, and even, let's say, how the material degrades or deteriorates or corrodes over a period of time. That is also important. So those properties, so this will be like the chemical properties, so to say. So all these properties are important for our applications. So that means we need to really know the structure, and we really need to know what are the properties and how this structure and properties are correlated. So that we need to understand. And that is basically the idea of material science. Okay, so of course, then the depending on its properties, so the performance or its application will be decided. So if you want to use it for you want a material with a good electrical conduction, so probably you will choose a material with a high conductivity or a low resistivity. So you have to design a material based on the structure, so that you can control the electrical property of the material, and that you will use in your application. So the material science is kind of will basically um, the second and third component comprises the material science aspect. So we are looking at the structure and how that structure affects the properties of a material. So the properties, these are like physical properties or chemical properties. Sometimes it's also called as functional properties. So how that is affected, so that is what we need to understand in material science. The other two components, the processing and performance, is more towards the application or more towards the engineering part of the material science. So that's why sometimes this term is used, material science and engineering. So a material engineer would look at how the application is depending on the structure and the properties. He will choose a particular form of application and then make a device or some form of this material for, like, he can make, for example, a tool to cut something. okay, to machine something. Like if I want to make a bottle like this, okay, so I need to precisely cut a shape or a material into this shape. So for that I need a special kind of tools. Now how that tools will be made, how those machines will be made, so that will be part of the engineer. So similarly, if I talk about a chip which is being used in your smartphone or in your laptop or your computer, so that chip, what kind of material and what are the properties, semiconductor material that you somebody is or need to make a good transistor. So with a good transistor characteristic, so that material science will scientist will look at, but then the engineer will use those chips for making like a smartphone or some device like for example your smartphone or your laptop or some other device. And recently, the fifth component has been introduced, that is reuse and recyclability. That means all the materials, whatever you are using for making a product, so that material has to be should be able to recycle. So that is a goal right now because of environmental situations, and that is also a big aspect in material science research as well. Okay, so I said that the material science aspect is mainly looking at structure and property relation. So that is the correlation between a structure and what is the property. So here I am giving you an example how the structure affects the property of a material. So the figure or the picture what you see is, you see some kind of disk. So the left hand side is completely transparent, so you can read what is written underneath. The center one is partially transparent, so semi-transparent, so you can read but not completely. So you can see that means some light is being transmitted, but not all the light. So it is kind of diffused. And on the third disk, you see nothing. So it is completely blocking all the lights. So you see nothing underneath. So it is basically opaque. But all three materials are from the same. This is aluminium oxide. Okay, so this is Al2O3, the same aluminium oxide. This is same in all three cases. But why one is transparent, the other one is semi-transparent, and the third one is opaque? So that is where the optical properties are now different. So material is same, but because there is some underlying structure which is different in three materials, so that now decides the optical properties and makes it transparent or opaque. So what are the structure? So the highly transparent one is basically it is a single crystal of aluminium oxide. So we'll look at what the single crystal means. Then it is the middle one, which is semi-transparent, is a polycrystal. So that means you have many crystals, small crystals, but they are oriented in different direction or different orientation. So that's why what you get is a polycrystal, and that there is a diffuse scattering of light that comes from like when you want to look at the what is written underneath. So this diffuse scattering is due to this, you have this polycrystals or grains, so to say, and they are separated by some boundary. Now there will be some scattering at the boundary, so which spreads the light, and that's why you are not able to see what is written underneath. So it makes it semi-transparent. And in the third one, this is an interesting structure. So this is a polycrystal, but it has designed pores or voids. Now, when you are looking at it, you don't see those pores or voids. So that means they are very, very small. Okay, so you cannot see it with your naked eyes, but there are pores which you can see if you look it under an electron microscope, for example. And these voids make sure that light even gets much more scattered, and that leads to makes it completely opaque. Okay, so this is how the structure can control the property of a material, and it is the same material. So there is another example here. So we take, for example, carbon. Okay. So the earlier example was aluminium oxide. So you have aluminium and oxygen, but also you can take a single element like carbon. You can make it in two different forms. So crystalline and amorphous. So crystalline means you have a regular arrangement of the carbon atom. So amorphous is like you have random arrangement of the carbon atom. Then in the crystalline form itself, you have different form of carbon, how the structure is. So it can be in a structure what we commonly call as diamond structure. You have a structure which we commonly call as graphite. So graphite that you use in your pencil. There is now another form of carbon, that is fullerenes. So these are all nanostructures. So fullerene, carbon nanotubes. There is also nowadays 2D carbon material that is called as graphene. So various forms of crystalline carbon exist, and they have all different properties. For example, diamond is one of the strongest material, but graphite is not. Graphite is can it's brittle. That is why you are able to write like your pencil with which is made up of graphite. So it can break and you can write it easily. But now instead of using graphite, if you use a diamond pencil, so you will never able to write. Even rather than the diamond, one will be used to cut or make a scratch on some, like even a harder object. So it will not break that easily. So same carbon atom, but they're arranged in a different way, and that leads to a completely different property. So similarly, this is like the example. The it is a diamond is really hard and graphite is brittle. It is the mechanical property. Even if you look at, for example, the electrical property. So diamond is a perfect insulator. Okay, so it's really a good insulator. So it will not conduct any electricity. But graphite is a relatively good conductor, so it will conduct electricity. So due to just how the carbon atoms are arranged in the crystal, so that completely changes the physical properties of the material. So similarly, if I go to fullerene and carbon nanotubes, so which are kind of a nanostructures, so which will be in the dimension of below 100 nanometer. So in fact, it can be 10, 20 nanometer in that range. So in that case, you have a completely different kind of electrical conductivity. In fact, in carbon nanotube, you can have a conductivity which depends on the direction in which you apply current. So it could be a semiconductor, it could be a metal. So very interesting electrical properties.
Sir, carbon nanotubes and fullerene are naturally occurring or
No,
make
yeah, that's a good thing. So all the material may not be a naturally occurring material. So diamond is you can find in nature. Graphite, of course, you find in nature. But this fullerene carbon nanotubes, they are all made in labs. Okay, so that is where the processing comes into the picture. So how you want to process, so it will be different. So diamond will be processed in a different way. So you can also produce diamond and graphite in lab as well, as well as in nature. But fullerene, carbon nanotube, graphene, so the other materials you need to grow it in a lab. So similarly, if you look at amorphous material, carbon, it becomes amorphous, and then it is in the form of a charcoal, a coke, which you burn like a fuel, carbon black. So this is used in forming some carbon structures, carbon foams. Again, completely different mechanical properties, thermal properties, everything different. So the same carbon has a, based on how the atoms are arranged, gives rise to various interesting properties. So this is what a material scientist is looking at to understand why it is like that. Okay, so we will look at certain classification of materials before going into the deeper aspects. Uh, so already you got an idea. There are materials which are, they have good. I mean, you can keep it into a certain category depending on their properties, their physical properties. Okay, so on base of that, so we have basically four different type of materials. So one we call as metals. So metal, for example, we have copper, aluminium, gold, silver. So these are all single element. You can make, then mix some of those metals together. Okay, so what we'll call as alloy. So alloy is like a solution we are making by mixing two different solids. Okay, so what we call it is as a solid solution. So we can make different form of this alloys by mixing two different metals. So these are all form under one tree. Okay, so that's what we categorize as metal. So then the second type is ceramics. So ceramics are basically some form of oxides, some form of nitrides. They are phosphides. Okay, so these are metal nitride, metal oxides. Okay, so these are called as ceramics. So ceramics are really very hard, and we will see some of the properties, how this is how these properties can be used to differentiate between different materials, this material class. So the example of ceramic is barium titanate, lead zirconium titanate. So these are very good uh, ferroelectric or piezoelectric materials. Then, of course, you have traditional ceramic like porcelain, like plates that is made of ceramics. There are many magnetic oxides which are ceramics. Then there is stone, different form of stone. So these are all comes into the ceramic. And normally ceramics are highly resistive, and the corrosion rate will be really so they are really strong or mechanically strong, hard, and highly resistive. So then there is another type, polymers. So these are all for example, you are using a lot of plastic. So these are all polymers. Okay. So any plastic bottle or any plastic like a polythene that you are using. So all these are form of some polymers, and they are also different forms. So this is another class of material. And then what people have done, that they're mixing like, so these are all three distinct features, no, metal, ceramic, polymers. But what then people tried mixing this metal ceramic, or maybe ceramic plus polymer, or metal plus polymer. And why they want to do that? So by doing that, so probably you can get the best characteristic of metal and the best characteristic of the polymer. So let's say if a polymer is really flexible, because you can make it flexible, but it is not really conducting. So if you incorporate metal, so you can make it a conducting as well as flexible. Okay, something like that. So that is what we call as a the fourth class, that is the composites. So you can mix any of these two, and that will lead to a property which even may not be present in metal or polymer. That is also possible in composites. Okay, that is also an interesting feature. Some property will be different, which is not even present in the parent compound that you have taken. So that's why people are also making these composites. That is also very, they have a lot of applications as well. Okay, so as I said, the distinction between this clear different form or classes of these materials, ceramic or metal or polymer or composite, one can see it in their properties. So here, this is an example of a bar chart. Okay, so where we it represents a stiffness. Okay, or stiffness means this is the Young's modulus. That means if I want to deform it, so how difficult it is to deform it. So higher the value, so it will be difficult to deform it. That means if I apply a force to bend it or extend it or deform it will be difficult. Okay, so if the value is high. When you look at this section, so metals are typically have a high Young's modulus, so stiffness is quite high. So ceramic is also quite high stiffness, but polymers are very flexible. Okay, they can you can easily deform them. As you have used, as I said, polythene or a plastic bottle, so you can easily deform it very easily. And once you deform, so probably it will be if you apply too much force and deform and break it, it will easily break. Ceramics, so some are highly very strong. So silicon carbide, like what we in the top you see silicon carbide. Uh, this aluminum oxide, silicon nitride. So they are very strong, high Young's modulus. And look at the scale. So the scale bar is in logarithmic scale. Okay, so we have 10, 100,000. Okay, so this is that's why even if you see a small jump in the value, so that will be few orders of magnitude change. So glass is another ceramic, but it also breaks quite easily when you are deforming. So this is still a ceramic, but it deforms quite easily. So this is a class like a property which defines, let's say, different form of this materials. Now, similarly, if you look at a strength, okay, so you also create this bar chart. So metal will be falling under one particular bar, ceramic under one particular bar, polymer like they have the strength is really less, as I said, so they are very easy to deform, so very easy to break them. So now let's look at electrical property. So electrical conductivity, if you look at, so this is again we have metals, then ceramics and polymers. They have usually a very small conductivity, and you see the scale here on the left hand side. So scale is so typically metal. The conductivity varies from 10 to the power 4 to 10 to the power 8. Okay, so it is in ohm meter, ohm inverse, meter inverse. And if you look at ceramics, it is like 10 to the power minus 8, minus 10. So there is, so in one end for metal, it is 10 to the power 8. And the other end for ceramics and polymers, it is 10 to the power minus 8. So the difference is quite huge, 10 to the power 16 orders of difference. Okay. So that you can imagine how, why these materials are, I mean, the property is defined by what kind of material is there. So based on the electrical conductivity, so we have a new form of material, a class of material, which we call as semiconductors. So where the conductivity lies in between metal and ceramics and polymer. So that again a new class of material uh, emerges when we are looking at the electrical property. But the semiconductor as a class of material we don't discuss when we are discussing about the mechanical properties. Okay, so this aspect comes only from the point of view of electrical property. So similarly for thermal or optical property you might be having a different division or classes of materials. Okay, any question so far?
No,
No.
sir.
So nowadays, when we look at the class of materials, so what we call it as an advanced form of materials, and this advanced form has many different nomenclature, uh, and this advanced material, what will be called as advanced material may vary depending on who is talking about it. But broadly, a advanced material is a material which is being used in a very advanced technology. So that is kind of a broad consensus. So you can say any material that is used in advanced technology, so we can call that as an advanced material. So for example, transistor is an advanced, if I use a silicon based transistor, so that is an advanced material because it is being used in my computer chip to do the processing for memory. Okay, so that is the advanced material. So nowadays there are plenty of these advanced materials, so quite huge. Uh, Particularly the materials you can make in a form of nanostructures or nanomaterials in form like depending on it can be a ceramic, it can be metallic, it can be a semiconductor, it can be a polymer. So in nanostructure form. So this is most likely will be called as a advanced material. And of course there are also new form of alloys and materials which are being used in advanced technology, for example in aerospace, in like electrical vehicles, energy, the materials that are being used in electrical vehicles, or in transportation. Okay, so these are all will be part of advanced materials. Okay, so I'll just take a break before we move on. If you have any question uh, before we go to the next topic.
Sir, among these materials, we can only I can recognize three, four things. All other things here in our syllabus are
No, no, no. I'm just saying, no, everything is not in the syllabus. So it is a overview of these advanced materials. So maybe we will, I will talk about few advanced material related to semiconductor, related to superconductor, then related to magnetic materials and optical. Okay. So some of
this
the advanced material that is with very interesting this optical or magnetic or electrical properties I will discuss.
but these names are really interesting names. When you read them, you think
Yes,
what are the material?
I mean these are all itself yeah, they are advanced in the sense each topic will be each one subject. Okay, so one full, so you cannot cover it in one lecture. So each topic, if you really want to understand, so thin film, for example, so thin film, how you can make a thin film, is itself it's a course. So one can give an overview, but you cannot really go deeper into that.
I was seeing, sir, you have written one paper on thin film. I was
Mhm.
searching about. You have done some
Ah,
research.
yeah, so in my case, the thin films I made, so you can make it, make thin films using, for example, chemical methods. You can also make thin films using physical methods. Okay, so physical methods are normally you use something called as a vacuum technology you need to use so that you can make a thin film on a substrate. You can grow thin film on a substrate. So this is a different technique. Uh, then the chemical process is a different technique. So if you are interested, I can give a kind of a overview of that thin film synthesis. I mean, these are all part of the course, but everything cannot be uh,
Yes, sir. Yes.
discussed or completed here in this limited
Yes.
time. Okay, so let's then look at a, a so so far I just gave a kind of an overview of all these different types of materials and so on. But as I said, in material science, so what we are interested in is we want to see the structure and then we want to relate it to its property. So let's look at how we can understand structure in a material. So when we talk about a material, so you go to the atomic scale. So what you have is nothing but some kind of, you have to have a bonding between two neighboring atoms so that they will stay together, and then you form a molecule and then the solid. So that means if I want to make a material, so I need to have some kind of bonding between the atoms. So this is like we are going into a more fundamental aspect of the materials now. So uh, we can say the atoms or molecules are the building blocks of our solid, and whatever property that we are talking about is related to structure or indirectly, or it comes from what kind of bonding is there. Okay. Uh, so if I take, let's say, just to give you an idea, if I take salt, okay, so that is what you use at home, okay, and you put it in water, right? You can just mix it, and so you get a very good salt water solution. So it dissolves in water very easily. It is a solid material. Now if I take, instead of this salt, if I take just like a charcoal, or if I take like a wax, like your candle wax, if you just take and you put it, it is not going to dissolve. Now how easily it can get dissolved in water, so depends on what kind of bonding it has. So this is somehow related to a little bit of chemistry as well, because whenever we talk about bonding and those kind of things, so chemistry is it is part of the chemistry. But here we will understand this formation of bond from a very physics point of view. uh, so to have a bond, so that means two atoms, they are bonded to each other, means they are close to each other, so there is some kind of interaction. Okay. So what kind of interaction it could be? The interaction only can be through some electrons, because these atoms have electrons, nucleus and electrons, and normally electrons, they surround the nucleus. So whenever two atoms come closer, so there will be interaction through this electrons. Now once you have, and electrons and nucleus, they are all charged particles. So if they are charged particles, you will have a electrostatic interaction. That is quite obvious. So you will have some electrostatic interaction, and depending on the charge, so if they are a similar charge, there will be repulsion. If they are opposite charges, there will be attraction. So you will have, so when you are bringing two atoms together, that means the charges together closer, so there will be a repulsive force as well as an attractive force. Both forces will be there. So the repulsive force will be between your electron electron, let's say, or nucleus nucleus, but there will be attractive force between electron and nucleus. So if I take two atoms A and B, so electrons of B atom will get attracted to the nucleus of A atom. So similarly, the electrons of A atom will get attracted to a nucleus of B atom. So that is, so new form of attraction and repulsion forces will be there. Now at certain position, so it is possible that you, the net force, they will cancel each other out. So this attractive and repulsive forces, they will cancel each other out. So you will get a zero force, so which we are writing as Fa. So here Fa and Fr, so represent the attractive and repulsive force respectively. So at equilibrium, this Fa plus Fr will be zero. So this is again represented on the top graph. So on the x-axis, we have the interatomic separation. And as we change this interatomic separation, so interatomic separation means the distance between two atoms. So if it is infinite, so there will be no interaction, so the force will be zero. But as you bring, so at certain distance, so there will be a repulsive force, so which is in the bottom, the blue one, so that is the repulsive force. And on the top one, you see an attractive force. uh, and because of these two forces, so you will have a resultant force, the net force, which is given by the blue color line, and this force will be zero at a particular distance r0. Okay, so that force or the position where this force is zero, net force is zero, so that is known as your bond length. So that means this is the equilibrium position, and atoms will prefer to stay at that position, and they will form a bond. So that is the bond length. So from this force, you can also calculate what is the energy. So simply how, so this is the energy what we are talking about is the potential energy. So this you can easily derive by taking a first derivative with respect to the distance between them, r. So this net force is nothing but minus dE by dr. So E is the potential energy. So again, so there will be a potential energy which is due to attractive potential energy. So because of the negative sign, so the force, attractive force, is in the upper half of your graph here, but the attractive energy is the bottom. So that represents your attractive energy, and repulsive energy is on the top quadrant, the first quadrant, and you get a net energy which looks like something like a U shape, but again towards when it goes to infinity, so it goes to almost zero. And at this r0 where this equilibrium position is, so you get a certain depth of the energy, and that energy will call as a bond energy. So that means once the atoms are at this equilibrium position r0, so they will be really stable, and they will have certain potential energy, of course. But if I want to break it now, so I have to give this much energy E0 so that I can break these two atoms apart. So this is how, in a fundamental, very general way, you can understand how the bonding forms. So now this bonding is not between only between one and two atoms. So it can be between one and four, one and three, one and five, or two and four, two and three. I mean, many different atoms now will form this kind of bond, and then they will arrange in certain way and build the solid. But the first point, they have to form a bond, and this is a very a general way how you can understand how this bond formation happens in solid. So this is quite important that you understand this. So next we will go to different types of bonds. Uh, so as I said, so the bond formation is nothing but there is some interaction between electrons or a sharing of electrons. So somehow the electrons are involved in the bond formation process because they are the outermost, mostly the outermost electron, because they will see the neighboring atom's electron immediately or first compared to your nucleus. So here is a classic example of how about the ionic bond, so which you know from your school days as well. So you have sodium and chlorine, and now in order to have a stable electronic configuration, so sodium is the atomic number is 11. So the electronic configuration, you have one electron in the outer shell. So now if this electron goes to an atom which wants one atom so that it can fill its external outer shell, so it will easily accept that, so which is the chlorine atom, so which has 7 atoms on the outer shell, so it will take one more and become 8, a fully closed cell. And that's how this bond formation happens. So Na plus and Cl minus will form, and you have a bond. And now this interaction between, because you have two ions, so now there will be a attractive force between them. And to keep this attractive, so you always have, so sodium will be surrounded by the chlorine, negative chlorine. So similarly chlorine, if you look at any chlorine ion, so it will be always surrounded by sodium atom. Okay, so that you have a positive attractive force between them, and you form this big NaCl solid or a crystal. So if you look at the potential energy, what you see in this case, as we discussed earlier, so you see the interatomic distance. So if R is infinite, so there will be no potential energy, or maybe a little bit of potential energy, very small. But as you bring them together at equilibrium, so in this case this equilibrium value is 0.28 nanometer. Okay, so that is the bond length, and you have a, the force will be zero, and you get a net energy which will be able to keep the bond together without breaking that, which is of the order of minus 6.3 electron volt. Okay. So that means I have to give about 6.3 electron volt energy per ion, so per NaCl ion, so that I can break their bond. Okay, and so this equilibrium separation is 0.28 nanometer. So you have to so this bond length is quite small. So this is typically what happens with ionic bond. Oh yes. So one thing which in this case, when you are writing the energy, so the attractive energy is normally written as minus A by R, and the repulsive energy is written by B by R to the power n. Now A and B are normally constants, and so the negative sign here represents the attraction. So that's why you have a negative sign, and positive sign represents the repulsion. So this n can is also a constant, but will be different for different ionic bonding. Okay, so if I take, for example, HCl or HF hydrogen fluoride or any other ionic like material, so this n can be different. But the attractive force is normally it will be a Coulomb attraction. Okay, so Coulomb attraction means if I know what how much charge is there, so q1 q2, so here q1 q2 will be 1, so you have uh, one more electron in chlorine and one less electron in a plus, so one positive charge, one negative charge. So q1 q2 by whatever the distance, this 0.28, that equilibrium distance, so you divide, so you can also calculate what is the electrostatic, the attractive force between these two. Okay, so the next type of bonding is covalent bonding. So which is basically all about sharing of electrons. So now it is not only the electron necessarily has to be exchanged, but they can be shared, and that will also lead to a kind of bonding which we call as a covalent bonding. So uh, remember, this ionic bond will be a directional in nature, uh, and covalent bonding is can be in any direction. Uh, okay, so one thing which is missing here, yes. So you have a sharing of electron. So the top one shows a simple sharing of like hydrogen and hydrogen, how the hydrogen molecule forms. So you have two hydrogen atoms, they share one electron each, and you have a two electron per hydrogen molecule. But if I bring now the third hydrogen, for example, if I bring that, so they will not form a H3 molecule, because it is not fulfilling the so the cell will not be anymore fully filled, but you have one extra electron, so that leads to so H3 molecule will never form, so you have only H2 molecule. But another interesting, which is more relevant for materials, is this hybridization process. So this sharing of electron is not only doesn't happen just like a simple in hydrogen molecule, but it could happen through a hybridization process. Again, hybridization term comes from the chemistry. So where you have here, we I'm giving an example of a hybridization of sp3 type hybridization. So what you have is, let's look at, so you have 1s2, 2s2, 2p2. So this is a carbon atom, for example. Okay, so we have carbon atom. So on the, if you look at the right hand side, so you have 1s2, 2s2, 2p2. So that means one of the p orbital is empty. So what this when the carbon atom wants to form a bond, so it would like to have a situation where it undergoes this hybridization, sp3 hybridization, which leads to a formation of four sp3 hybridized orbitals. Okay, so instead of having this independent 2s orbital, 2px, so you have 2px, 2py, and 2pz is empty. So instead of doing that, so what happens, this one of the electron from 2s goes to 2pz, and they form a sp3 hybridized orbital. And in that case, all this sp3 hybridized orbital will have the same energy. So earlier the 2s has low energy compared to 2p, but after hybridization, what happens? So you have four hybridized orbitals, and all four will have electrons, one electron each, which they can share, and they have the same energy. Now, if another hydrogen atom, for example, comes nearby, so now it will form a carbon will form a covalent bond with hydrogen. Okay, so it will now bond with four hydrogen atoms, because there are four sp3 hybridized orbitals available, each having one electron they can share, and the hydrogen can contribute one electron, and they'll easily form a bond, which we call as the formation of methane, CH4. So this is also true for diamond, for example. We talked about diamond, the structure. So the diamond, the carbon is also a sp3 hybridized carbon. So the carbon, now in diamond, you have a bond between carbon and carbon. So not carbon and hydrogen, but carbon and carbon, because it's only carbon atom. So now one carbon atom forms this sp3, four sp3 hybridized orbital. The second carbon atom also forms four sp3 hybridized orbitals. Now each hybridized orbital has one electron. So they will share, and this carbon-carbon bond will form. So this is a covalent bond. And typically this angle is about 109.5 degrees. So the angle between the bond, this sp3 hybridized orbitals, is 109.5 degree. So this is and this particular bond, this sp3 hybridized bond in diamond, leads to its property. This is because makes it really hard. So it will be very difficult. Hard means it will be very difficult to break this bond. So the bond energy will be quite high, and also it makes, because all the electrons are now part of the bond, so there is no free electron, so to say. So the conductivity is really small. So this covalent bond, in context of carbon, you don't have the sp3 hybridization, you also have the sp2 hybridization. Okay, so sp2 hybridization, again you have this carbon, you have 2s, like all the four electron will go. But in this case, what happens in sp2 hybridization, so you have now three sp2 hybridized orbital. So these three sp2 hybridized orbitals will have the same energy, and the pz will have a higher energy. So this, whether sp2 or sp3 hybridization will happen, again depends on how the material is being processed. So how you are making the material. Okay, so if you apply a too high pressure and a certain pressure or certain temperature, so you will have a formation of sp3 hybridization. But if you have a certain a low temperature or a pressure which is atmospheric pressure, so you have a possibility or probability of having a sp2 hybridization. Now again, the same carbon atom, if there is a sp2 hybridization, so that will form these three bonds, okay, sp3 hybridized bond, and these are all in one plane. So you can see here in the image, so you have sp2 hybridized, so the bond angle is 120 degree, and they are in one plane. Okay, so this is like a forming a hexagon. So now one carbon atom comes, the next one, so now they will share the electron or the orbitals, and this sp2 overlap will happen, or sharing of electron will happen, and you get something called as a graphite. So graphite has a sp2 hybridization. So diamond has a sp3 hybridization, and graphite has a sp2 hybridization. And this hybridization decides, so now the bonding decides what is the property of the material. So graphite then becomes brittle. Why? Because you have one electron, this pz electron, which is not part of any bond yet. So when we talk about carbon carbon bond, so this pz electron can now jump from one orbital to the other orbital easily, and due to that, graphite will have a much higher conductivity. And it will also develop a very interesting kind of bonding between two layers of a carbon. So I have a hexagon like here you see one hexagon. So each hexagon, the point represents a carbon atom, for example, right? So carbon, so there is one carbon, one carbon, one, two, three, four, five, six carbon. So you can also imagine there will be another same hexagon over it. Okay, and this is how it will extend from uh, on top of each other, and then there will be a very interesting kind of bond between the layers. So which is nothing but what you call as the van der Waal interaction. Okay, so this is the interaction of this pz electrons, which will lead to this weak, very weak interaction, the van der Waal interaction, and that makes it like you get a layer, like hexagonal layer on top of each other, and that changes the property of graphite completely. Nowadays what people are doing, so instead of growing only like several stack of this hexagon, so you can only make one stack. Okay, so that is what we call as a 2D graphene. Okay, so this is only the one hexagonal sheet you take, and that we call as a graphene, so which is being used very extensively for many different applications. So graphene, if you look at just google graphene, so you'll see lots of application, which probably I think the next generation or the next century, one could call it as a century of carbon based materials. It is possible. Okay, so this is clear, this bonding. Oh, so this one should be, so this ionic and covalent is clear, and graphite and diamond.
Yes, sir.
Okay. uh, so here there is a mistake, so this should be not ionic bonding, but this is a metallic bonding. So I'll just correct quickly so that you don't have a confusion. So the third type of bonding is a metallic bonding. So this is also the name suggests. So most of the metal will have this kind of bonding. And why this bonding happens? Because when you look at a metal, so normally they have something which we call as a valence electron. Okay. So this when you bring, for example, two copper atoms, so they will not form this ionic or covalent bond. But what happens? So this electron will be shared with all the carbon or copper atom in the solid. So that means if I take 1 mole of copper atoms, so each one will contribute one electron, and this electron will be kind of free and will be shared with everyone. All this 1 mole of Avogadro's number of copper atom. That way, it has so this electron basically acts like a glue. Okay, so this free electron acts like a glue and holds all these iron cores. So now if I take one electron from the copper atom, so copper becomes copper plus and electron, one electron. So now each copper plus now is glued with each other due to this free electron. Okay, so you have a sea of valence electron, and within that sea, this sea of valence electron acts like a glue and connects all these ions together. And this is what the metallic bonding is all about. Now since you have lots of these free electrons, so you have a very good conductivity in this material. So these free electrons, whenever if you apply electric field, so these free electrons can easily move and you get a good conductivity. So most of the metals will have this kind of bonding. So copper, silver, gold, aluminium, magnesium. Okay, so these are all will be having this metallic bonding. Yeah. So there are other. So the covalent, ionic, and metallic bonding are mostly they are called as a primary bonding. So they are the most important bonding that you have. There are some secondary bonding, so which is very weak. So here one example is the van der Waals bonding. So this is also very it is prevalent. It is not like although it is weak, but it doesn't mean that there is no use of this van der Waal bonding or van der Waal interaction. So, for example, when we look at a surface tension, so this is all due to a van der Waal interaction. And if I want to put any tape or a adhesive on another surface, okay, so there will be a very weak bond, and that bond is a van der Waal bonding. Okay, now the origin of this van der Waal bonding is also very interesting. Uh, it is again purely a electromagnetic in nature. So which is due to the existence of atomic or molecular dipoles. So you have, when you will bring, let's say, two dissimilar materials together, okay, so in that case what you have, you can modify the dipole moment of the molecules. So dipole moment will be always there because you have some charges. So you have nucleus and electrons. So that means you have some charges. If by any means you can distort this charge distribution, so you can make it asymmetric, so immediately you will have a dipole. Okay. So there are three ways how this van der Waal bonding manifests in materials or develops in materials. So the first way is what we call as a fluctuation induced dipole. So ultimately, if you want to have a van der Waal interaction, so you need to have a dipole moment. So electric dipole moment. So if an electric dipole moment develops, so then there will be a dipole and it will interact with a neighboring dipole, and that way the bonding will be there. But because this dipole interaction energy is very small, so that's why this bond energy is really small, and it is a very weak bond. It can break easily. So the first one, the fluctuation induced dipole, it can arise due to some random fluctuation of a molecule. So there will be always, we know these atoms are vibrating. Okay, so atoms are, these are all due to the thermal motion. So at any temperature, due to the thermal motion, so what could happen? Probably the nucleus vibrates slowly compared to the electron. So in that case, the charge separation, so there will be a formation of a dipole. So electron moves a bit far away from the nucleus. In that case, it becomes, so the charge distribution becomes asymmetric, and you get a dipole. And once that dipole forms, so if there is another symmetric molecule nearby, but due to this dipole formation, so it will be influenced by that, and again it will also deform, and there will be a dipole formation in the neighboring molecule as well. And then so these two dipole will interact together and form the bond. But the thing is here, so this is a fluctuation induced, so that means it is a dynamic kind of bond. So it is like kind of changing all the time. It is not like a bond has formed and it is fixed. Covalent ionic, so once the bond is established, it will be established as long as you are not applying a temperature or some other energy, you are not giving any other energy. So but in this case, so this bond could change or vary over like the surface, but there will be at some every moment there will be some kind of bonding, so that keeps the things together. So the second way of creating this dipole is the if you bring a polar molecule and induce the dipole. So what is a polar molecule? So polar molecule is something which it has an inherent dipole already. So water is a polar molecule. So HCl is a polar molecule. So it has a permanent dipole moment. Now, if you bring such a molecule close to a symmetric molecule, which is doesn't have a dipole, but because of this asymmetric charge distribution, so again, it will induce a dipole in the symmetric molecule, and then there will be a van der Waals interaction between the polar molecule and the induced dipole. So that is one way of making this van der Waals bonding. So another way is like if you have permanent dipole, so like HCl or HF. So if you bring two of those similar polar molecules, because they already have some dipole, so now they will attract. And what you have in this case, like in the third case, what you see, you form something known as a hydrogen bond. So this hydrogen bond is a form of van der Waals bonding. This is very useful, very interesting in context of water. So in water, you also have a hydrogen bond, but this hydrogen bond leads to, so when you freeze water, so what happens? So normally, whatever you freeze, so you say the density increases and the volume decreases. But in case of water, so the reverse, the water, the volume increases and the density decreases.
Ice floats.
This, yes,
That's why ice floats on water.
ice, yes. So that is why ice floats on water. And this formation is due to this formation of hydrogen bond when you cool it down. So you have a more bond formation between the hydrogen, the oxygen with the neighboring hydrogen. Okay, so in a water molecule, you have only the bond between, so one oxygen with two hydrogen. But when you go to ice, now this oxygen will also bond with the neighboring hydrogen, and in it will form this hydrogen bond, which in such a way that uh, it increases its the volume and decreases the density. Okay, so this is a very peculiar case for water, but all other cases it is always happens the other way around. Okay, so this is a, yeah, another thing which I want to point here. So when we talk about this type of bond, so definitely the bond energy is different for different materials. So even if it is a ionic bond, for different material, the bond energy will be different. Even if it is a covalent bond, the bond energy will be different. So how do we know experimentally that the bond energy is different? So the best way to find out whether the bond strength, the bond energy is high, or the bond strength is more, or is it strong or weak? the best way is to look at the melting temperature. Okay, so any material which has a higher melting temperature always has a very strong, the bonding is really strong. Okay, and anything which has a low melting point, so you immediately say the bond strength or the bond energy is low, bond strength is weak. Okay, so this is the best indication. So in the book, any literature you look at, so you can look at melting temperature and you can immediately see how the bond strength is of that material. Uh, so diamond, graphite, so they have a very strong bond and they have a high melting temperature. Many of the alloys, metals, so the bond is really strong, so melting temperature will be high. But if you look at, let's say, aluminium is a metal, but the metallic bond is weaker, so it has a lower melting temperature. Okay. Yeah, so another very interesting aspect is this mixed bonding. So mixed bonding happens because we are you may not have, because there is a difference in the electronegativity of different elements that are involved in the bond formation. So because of the electronegativity difference, so you may not have a pure covalent or a pure metallic or maybe a pure ionic bonding or maybe a pure van der Waals bonding. So it could be something in between. So this is what we call as a tetrahedral structure. So tetrahedral representation of this mixed bonding. So that means if I go along any axis of this tetrahedron, so I will find out it will be a mix of covalent or ionic or metallic or ionic. So if I go along one of the edges, so that is what it will represent. Now on the right hand side, you see like if I take metal, so it will be purely metallic. But if I take some materials which are purely metallic and make a alloy with something which is ionic in nature, so what we form something known as a intermetallics. Okay, so this is a class of material intermetallics. This is a form of alloy. So similarly, if I take, for example, ionic and a pure covalent bond. So most of the ceramics will be somewhere in between. So they will be not perfectly covalent and not perfectly ionic. So some percentage ionic will be there. So this percentage of ionic you can actually calculate using this expression here given. So this XA and XB here uh, basically represent the electronegativity of the materials or the elements. So that you can get from the periodic table. So one can calculate how much percentage of ionic, uh, what percentage is ionic in nature in a bonding. Okay. Okay. Anything from this part? Okay. So we will move to the next part of this structure, because we are now talking about the structure. So now the structure depends on the bond, we said. So if we take one atom, the second atom, so we will have some kind of a electron exchange, electron sharing, or this electron can be shared with all the ions. So we can have different form of bonds. uh, but how do we create then a ordered structure out of it? Okay, so that is what this topic will tell you, which comes under something called as a crystal structure. So again, here we are going from atom, a molecular, to a many atoms. Okay, so we are now trying to arrange all these atoms in a regular order, or what we call as a periodic order, and it will be a long range order. So long range means it will be like it can extend up to a micrometer or even millimeter, and that will lead to the formation of a crystal. So the crystal is basically defined, represented very nicely in a geometric fashion, because we now have a regular arrangement of the atoms. So we can assign a geometry to it, okay, so which we call as a lattice. So I think these are the things which you already been introduced, I think, in other courses. So I'll not spend more time here. So you have basically a lattice. So that means you have points in free space. Okay, so these are just represent points. Then each point will be, you can assign one atom or more atoms or a molecule, and then if you add these atoms or molecules to those points, so which we call as a basis, so then what you get as a crystal. Now, to represent this crystal, so what we have developed, we call it as a building block. Okay, so because we have again a repetition of these points, so we can take a building block and then repeat it in all three dimensions x, y, z, and create the crystal. So that building block we call as a unit cell. Okay, so this is normally represented in two ways. So the left hand side represents the hard sphere model. Okay, so hard sphere, why? Because what we are saying is, when we have the unit cell, so the two atoms or ions or whatever may be, so they will be really touching, just touching each other. Okay, which is not correct, but it gives a good mathematical representation the of this atomic or the unit cell picture. So this hard sphere model is quite useful in that sense. You can also use a soft sphere model that I have shown in the left right hand side, so which clearly shows how the lattice points are arranged. So it will be like a cube here. So this is a simple cube structure. So similarly, you can have a body-centered cube BCC crystal. Okay, and here again we have a hard sphere. So you have one atom completely within the box, the cube, and then you have atoms on the corners. And if you now repeat this unit cell along all the three dimensions, you create the BCC crystal. So similarly, you can also create this FCC crystal as well, right? So in this case, you have atoms on the corners as well as on the face of the cube. So now if you repeat this unit cell, you will create the FCC crystal. So another very interesting crystal structure is the hexagonal close packed crystal, HCP, where the unit cell is hexagonal, and you have so it is not anymore cubic but hexagonal. So these are all quite important unit cells. So the cubic and the hexagonal are commonly, very commonly observed in most of the material that we work with. So there will be some complications when you go to ceramics, for example, or polymers, for example, but you can define it using some of these hexagonal or cubic. By defining this unit cell, so what a lot of information we can extract. So you can calculate, for example, number of atoms per unit cell. So I think you have done this, you know this from condensed matter physics or other courses. So number of atoms per unit cell, number of next nearest neighbor, the volume of the unit cell, because once you know what is the dimension, you know what is the volume. So you can calculate based on the hard sphere model, you can calculate what is the relation between the axis, the lattice parameter, and the ionic radii or the atomic radii. Another very interesting uh, parameter, which is the atomic packing fraction, APF, that you can create, because that tells you how much of the space is empty in a unit cell. So if you look at, you can like you calculate. So what you will see that the maximum which you can the field of space using a structure is the face centered cubic FCC or HCP. So both will have about 74% you can fill up the space using the atom. So the rest 26% will be empty. But if you go to BCC, it will be about 50% or so. I think 56%. So another interesting thing about the crystal structure, if you know the crystal structure, so you can calculate this density. So this is a theoretical density, okay, assuming that your crystal is a perfect crystal. So you can use this formula and calculate. If you know the crystal structure, you can calculate the density, and then you can correlate it with, you can measure the density of the material as well. If you know what is the mass and what is the volume, so you can calculate. So then you can understand if you have any defects or any voids or any pores in the structure. Okay, so this is also a very useful parameter to derive or obtain if you know the crystal structure. Yeah, another very interesting aspect of this crystal structure is called as a polymorphism. Polymorphism or allotrope. So allotrope means you have the same uh, crystal or the same element or atom or molecule in the crystal, but it has a different structure. Okay, so the arrangement or the ordering of these atoms or molecules changes. So here is a very interesting example. So you have normally at room temperature the tin, okay, so Sn. So it is in a form of a beta form, so which has a color white. Now if we cool it down, so if it goes below 13.2 degrees Celsius, so it uh, now you have a very different like a FCC kind of distorted FCC kind of tin, so which is called as a gray tin. Okay, so this is a BCC, so white tin, which is BCC, and it goes to this FCC, distorted FCC kind of thing. So cubic, but a different crystal structure, and that changes its properties completely. So on the bottom you see a figure. So the white tin, which is in a form of a structure, now once you cool it down, so it just becomes brittle and easily breaks. Okay, so now again you see how the structure affect the properties, and again this structure here is because there is tin, only tin, nothing else. But now how they are arranged, so that decides the property. So this polymorphism is also quite there are a lot of other elements which also show or exhibit this polymorphism. So carbon, as I already said, is another very another example. Like carbon can be in the form of graphite, in the form of diamond, in the form of carbon nanotubes, fullerenes. So these are all also known as allotropes of carbon. So this is also quite interesting to know that a same element can exist in different structure depending on what is the temperature and what is the pressure and so. Okay, so we just discussed only the important like unit cell, the cubic and hexagonal, but there can be several classes of this crystal systems. So basically, we have divided into seven classes. So cubic, hexagonal, tetragonal, rhombohedral, orthorhombic, monoclinic, and triclinic. So how do we then define these crystal systems? So we use because again it is related to the geometry. So we define it in the basis of the axis that we have used. So the length of those axes. So in case of cubic, so we say the A, that is the lattice parameter. So A equal to B equal to C, and then what is the angle between those axes. So that will decide what kind of crystal system we are using. So if I have a cubic, so A equal to B equal to C, and alpha, beta, gamma. So what is alpha, beta, and gamma? So alpha will be so you have to first of all define the origin, then define a x, y, z axis, and then you can look at the angle alpha, beta, and gamma. So if it is between z and x and z, it will be alpha. Between y and z, it will be beta. and x and sorry, x and y it will be beta, and y and z will be gamma. So again, this definition of this angle, sometimes it is different for different books, but if you are sticking to one particular definition, you stick to that particular definition. Okay. So this, yeah. So for example, in this case, you can see. So if I define A, B, and C, so this is my A, B, and C axis. So the angle between A and B will be gamma. The angle between A and C is alpha, and the angle between B and C will be beta. So now, how you define your x, y, and z again depends on your convention. So you can normally what you do is you'll put this A as x-axis, B as y-axis, and C as the z-axis. So this is a typical convention. Okay, so when you look at the crystal structure, we need to find out few like as we said, so this is a geometry, so it's a mathematical representation. Now how do we find out different like a point on this unit cell, or if I want to find out like set of points, so that is a plane. Okay, or I want to find a particular direction, I want to define a particular direction. So how do we do that in a crystal? So I'll just give you a few example of this. So we have taken a very random crystal here, okay? So not necessarily cubic, and again, not so the A, B, C axis can be different here, okay? So that is what is being shown. So we have defined the axis. X is like as it is shown, Y is like Z, these axes are shown, and we have also defined the values. What is the parameter, cell parameter? Okay, so 0.48 nanometer, that is along x-axis, 0.46 along y-axis, and 0.40 along the z-axis. So A, so we can say A is in this case 0.48 nanometer, B is 0.46 nanometer, and C is 0.40 nanometer. Now the question is, we want to find a point which represents the indices 1 by 4, 1 and half. Okay, so this is a point we want to find out in this unit cell. So how do we do that? So this will tell you or help you in doing that. So we have defined the, so we will start with the origin. This is the point M here. Okay, so we'll start from point M, and we will go 1/4 along. So this first one is along a axis or x axis, the second one is along y axis, that index. So 1 by 4 along x, 1 along y, and 1.5 along z. So this is what we want to find out. This is again all a mathematics, that is coordination geometry that you have studied. So what we will do is we will move 1/4 along the x-axis. So along x-axis, the dimension is 0.48 nanometer. So that means if I take 1/4, it is 0.12 nanometer. So I go 0.12 nanometer along x-axis. Now along y-axis, I'll go exactly a fraction 1 unit completely. So that is 0.46 nanometer. I'll go there. So I'll reach this point. So from M to N I come, then N to O. Then I'll go along the z-axis by half. So half of the 0.4 is 0.2. So I'll go about 0.2 nanometer along the z-axis along this plane, and this point P represents this indices 1 by 4, 1 and half. So this is a coordinate of a point on this unit cell. Okay, so this is how you can find any point in the crystal. So this is again is we are defining the coordinate of a point in this unit cell by defining the axis. Okay. The second and interesting aspect is how we can find the direction. So, okay, we find a point. Now, if I join 2 points, for example, so I have connected this point to this point. So this is the tail, this is the head. So this is the arrow is pointing in this direction. So I want to say, what is the direction? Can I represent it using some index? That is also possible. So what you need to do is, you need to first assign the coordinates. So what are the x, y, z coordinate of the tail? Okay, so this is x1 is a, okay, because we are going by a distance a here. Y1 is 0 because there is no so y axis, along y axis there is no value, so 0. And also along z it is 0. So the coordinate of the tail is a 0, a 0 into b, 0 into c. Okay, now what is the coordinate of the head? That is this point. So this is a line along in the yz plane. Okay, so this is a line in yz plane. So that means x will be 0. And y2 is b because that is what you see. So you have to go by a distance b along y-axis to reach this point. And how much you have to go along the z-axis? That is c by 2. So once you identify that, so what you do is you take the coordinate difference. So this is what in this table we have written down. So x is 0a, this is for the head coordinate, y is b, z is c by 2. For tail coordinate, this is a, 0b and 0c. Now you subtract, so what you get is coordinate is minus a, b and c by 2. So next what you need to do is you have to multiply with a number so that you make everything as an integer. Okay, so not any fraction, so you keep it to integer. And what we have to multiply here to make everything integer, we have to multiply by a factor 2. So if you do that, so what you go get is minus 2, 2 and 1. So that means your direction will be 2, and then to show that you have a negative sign, so instead of putting it minus 2, so you put a bar over 2, so that represents 2 bar, then 2 and 1, and then you close it with a square bracket. This is important. Okay, so you have to, the minus sign will be represented by a bar, and you have to put a square bracket so that you say this is the direction of this line. So this line has a direction 2 bar 2. So you can do this exercise on your own by drawing a cubic crystal or any other crystal. You can do that. So also this is an example how you can make find a plane Miller indices in a crystal. Okay, so in this case we have a plane. So this is shown in this pink kind of shaded region. Now we want to find out what are the Miller indices. I think Miller indices already you have been introduced. So I'm just giving the example of this, how you can calculate so that you do yourself at home using some examples. So in this case, what you have to do is, because your plane is passing through the origin, so you cannot take that as a origin as that. So you have to put a new origin. So that's why we have drawn another origin O prime by displacing the unit cell along the y-axis, and then you will calculate where it meets different x, y, and z axis. So when you look at it carefully, so this meets x-axis at infinity. Okay, so it really parallel to the x-axis. Then this plane meets the y-axis at minus b. Okay, so we are now calculating with respect to this origin at O prime. So with respect to O prime, so it meets y-axis at minus b and z-axis at c by 2. So then you know the process of Miller indices. So you have to take the inversion, and again, so that means you will have 0 or sorry, you have, I think I have a table. Yes. So here this intercepts you calculate. So at infinity in A, minus b for y-axis and c by 2 for z-axis. to calculate the HKL, so what you have to do is you have to take the inversion. So 1 by infinity, that is becomes 0. So minus 1, so that remains minus 1. So C by 2 becomes 2. So then the HKL values, the Miller indices, becomes 0, minus 1, 2. And again, to represent the minus sign, so you write a bar, 0, 1 bar 2, but you enclose using a using a normal bracket. Okay, so not a square bracket or a curly bracket. So this is how you write the HKL value. So similarly, if HKL value is given, so you can also draw a plane. So you do some exercises. So these are some examples, like how a 001 plane looks like 110. So this is most of the time, this is what we are interested in, like 111 plane. So these are the different orientations of the plane that you will come across in a crystal. Another interesting aspect is the close packed crystal. So if you look at the arrangement of these atoms, uh, so on the left hand side, what you see is, so we have a a packing like a which is assigned a position A. Now the next atom you can put either, so you have two kinds of voids here. So one designated by B, so this creates one kind of void, and the point C creates another kind of void. So that means I can put atoms over B, or I can also put atoms over C. So this leads to a form of a close packed structure. So if I only put atoms on A and then on B and then repeat again on A, so what I get is normally a hexagonally close packed system. But if I put an atom on A, then I put the next set of atoms on B, then the next set of atom on C, and then repeat this sequence. So I will create this kind of close packing, which is normally called as a FCC close packing. Okay, a face centered close packing. Okay, so if I do this A B and A B A B repetition, so that is a hexagonal close packing. And if I do A B C A B C, so that kind of stacking is called as a face centered close packing. So both have, remember, both have the same packing fraction. Okay, but the number of units, number of atoms per unit cell, volume, everything will be different. So I'll just briefly discuss, and then we will discuss in detail in tomorrow's class on this. So we have, let's say, crystal, we said. So how these crystals actually form? Okay, so this is also interesting, uh, because this is a part of processing. Okay, so in the beginning I said, when we talk about material science, so we have four components. So one is processing, then structure, and then properties. So structure we have seen, so from atomic, like depending on how the bonding is, we have defined the structure. Now by arranging these atoms in regular way, so you create these crystals. But how this crystal formation happens, so this is a schematic representation of that. So what you have is basically you create, let's say, one or two unit cell. Okay, so they come close together, and as you cool down the system, so what you have is you grow like, so what you can imagine, so let's say, so uh, the shaded region that you see is kind of represents probably a vapor phase or maybe a liquid phase. Okay, so now what you are doing is you are cooling down. So by cooling down, what you do is you have a process called a nucleation. So you nucleate a crystal, one tiny crystal. Okay, so this tiny crystal, which is now represented by a unit cell like a square, so now it forms, And as you cool down further, so what it happens, so it will grow, so it will collect more and more unit cells nearby, so they will start arranging in a regular manner. But this nucleation process is random, so you have many such nuclei, okay, or many such crystallites which have formed and they are growing. So as you cool down further, so they will grow bigger and bigger in size. And now a situation will come, so where they will meet. But now, because the way they are oriented, so they are different, okay, so what happens, so what you get, typically what you get is something called as a polycrystalline material. So a crystal where the crystallites that have grown from your nucleus, so they are all oriented in different directions. So what you can see, so these squares, when they are put together, so now they are oriented, these blocks that you have created, they are oriented in different directions. So what you call this kind of picture is a polycrystal material, and what you call is one of those area or the crystal you call as a grain. And now these two grains are separated by something called as a grain boundary. Okay, so this is how a typical crystal forms. Now the question is, can we get so how a single crystal would look like, so how a single crystal can be made, or can we really see a single crystal? So single crystal means there will be no such grain boundary, so all will be oriented along the same direction. So is it possible? It is possible. So I'll just show you one picture. So this is actually a real iron, this is yes, so this is a iron, some form of a iron, which was, I think, was mined. So it's a natural iron, and you could see clearly, so this dimension is of the order of few centimeter, and this was naturally grown. So you see a very interesting perfect cube, okay, and also you see this imperfect part of the iron as well. So that means the perfect part represents a pure, it's a single crystal. So so iron is actually a cubic BCC structure. So now this BCC crystals have grown, and they have grown in such a big dimension, about more than about a centimeter, so that you see this huge tube. So this is a single crystal of iron which is grown naturally. But you can also have a process where this iron is grown in a polycrystalline mode as well. So what decides that, how it happens? So we will discuss in detail in the next class. So I'll stop for today. If you have any question right now, you can ask.
Sir, please suggest any book.
Okay. I think, yeah. So whatever I taught today, it is from this book. So Material Science and Engineering: An Introduction. This is by Callister. I think there are one or two more authors, but the primary author is Callister. So this is a classic material science book. Okay. So I will be following this book. So you can get a PDF copy of this and read. So whatever images that I have shown here, for example, so this image or whatever earlier images, these are all from this book. So it is a classic textbook on material science and engineering. So you can note down and get a PDF copy of this.
Thank you.
Okay, any other question? Okay, so if not, so thank you very much. So I'll stop sharing now. And yeah, so we will meet tomorrow. So if you have any particular like topic, so since you now know the book, and you know the broad topic that I outlined in the beginning. So if you have still some particular topic of your interest, you please mention that tomorrow. So I'll try to cover them next week when we have the classes. Okay, thank you. So